Okay, I'm going to get started. Again, welcome everyone. My name is Orkan Talhan. I'm an associate professor of fine arts at Weizmann School of Design. And I would like to welcome you to today's webinar, which I will be co-hosting with Deirdre Krieger, who is going to join us in a second. So tonight's webinar is about introducing, it's an information session with some lively content with three speakers that are coming from Penn. Our goal is to really introduce you the background of our webinar, how we started, why did we decided to do a robotics residency, robotics art residency at Penn, and what kind of things we can expect from it during the COVID times. And we eventually will hear from our speakers what kind of, and their research, what they do at Penn in terms of robotics and the creative applications of robotic technologies. And then after our speakers, we will have a Q&A session where you can ask us all kinds of questions about the residency. So without further ado, I'm going to share my screen and give you a little background about our webinar. So our event is organized, our residency is organized by two schools at Penn Engineering, the Perch Lab, the Perch Research Hub at Penn Engineering, which is about bringing research and collaboration across different engineering programs and centers at Penn Engineering. And the other group is School of Design, Weizmann School of Design, which is hosting 5 different design school programs from fine arts to urban planning to architecture and landscape architecture. Our event, our residency is supported by the SACS program for art innovation. So we received a grant last year to really pursue a residency program that can bring the different researchers of the schools, for Weizmann and Perch together, so that we can invite different creatives all around the world to come and explore creative applications of robotics at Penn. So today we are going to talk about our residency. We'll hear from 3 distinguished speakers who are currently faculty or researchers at Penn. And then we'll have our Q&A session. So to give you a little background of why we decided to undertake this opportunity, last year, if you are at Penn or if you are in Philadelphia, you might have seen this major exhibition that was organized by the Philadelphia Museum of Art, which was called Designs for Different Futures. It was an exhibition that brought together many different design pieces and all around the world that explored different applications of design and how they are relating to the future of technologies, future of our lives, future of the society, and so on. So I was a consulting curator of the show, and that gave me an opportunity to work with many different artists, engineers, and designers that engage with different aspects of robotics. So robotics obviously was not new to Philadelphia or Penn. At the University of Pennsylvania, we do a lot of different kinds of research. But when you look at the image of the announcement of the exhibition, it was also a key element for designers who really explored the critical applications of robotics as well. So the piece that I've shown you in the slide is called Raising Robotic Natives, which is about asking questions related to how intimately robotic technologies, automation technologies will come into our lives, and how much we can trust them. How are we going to actually let them shape our children's lives in 21st century? So this is not about promoting the robotic technologies in one particular way, but using them as a lens to ask really interesting questions about how much they're going to be involved in our lives. So Penn has many different research groups that make a lot of different contributions to the field of robotics. And a couple of them were featured as part of the exhibition as well. Now you're looking at Quarry, which was a collaboration with many researchers at ModLab, which is also part of Perch, and Simon Kim, who is an architect at the Weizmann School of Design. So the contribution of this project was to really ask questions about what are the values that shape the design process of robots? What kind of, how do they become socially, so how can they become socially aware of the biases that are shaping our interactions in the society? What's their take on racism? What's their take on immigration? What's their take on all kinds of deeper questions that shape our daily interactions? So Quarry is a robotic platform that allowed many members of the community to submit ideas, submit questions so that they can collaboratively design the behaviors of the robot so that they can use it as a research tool in their environments. Robotics is always about both utopia and dystopia at the same time. So this is one of the other pieces that we had in the show, which is the ultimate human-robot collaboration, maybe, right? It's about an exoskeleton that allows people with walking disabilities to gain a different kinds of agency together. So this work is also telling us about how far we can really depend on these robots when we have different ableisms that are shaping our lives. Robotics is not just a question of determining what are, are the algorithms, are these machines, are these materials, are these biological artifacts. We have a very open-ended and open-minded way of thinking about robotics. But today, our speakers will tell you what kind of robotics that you can explore at Penn from our perspective. Of course, it's also not very limited, but we are open to calling a lot of different things robots. And in this case, you're looking at materials that are designed with robotic agencies. They interact, they respond, they are programmed on a cellular level, on a material level, so that they also pass as sentient artifacts that are designed for robotic behavior. But as this is an art residency, it's also very important for us to mention that robotics is not only about celebrating a technological utopia or just privileging certain technologies over others, but also embedding them into our different kinds of artifacts, different kinds of questions, so that they also become part of our tools, part of our variables, part of our expressions, where robotics become a semiotic artifact that help us inquire critical questions about our social biases, fears, and desires in the society. So in our residency, we picked 3 seed topics that will invite the creatives who are going to come and work with us to think about how robotics can actually help us think about the future of labor, future of productivity, the future of work. How can it help us to think about all the kinds of inequalities in the world? How can we use it for social empowerment? And also more critically to think about how it can help us to think about the climate emergencies, the things that we need to do very quickly to be able to survive on the planet in terms of the climate change and its consequences. So the residency terms and all the ideas that we have about the project is listed on this URL. I want you to note it down because we use it as a communication point to reach out to a lot of you. We will have a mailing list sign up there if you are interested in hearing more about the kind of research, kind of projects that are happening at Penn. We will be posting them there as well. But very briefly, the residents, we'll pick 3 residents and they'll be given a stipend and materials and a housing budget. And if they are based in Philadelphia, the housing budget will be also included into their production budget. So it's a modest fee, but it will help us, it will hopefully help our residents to develop very interesting projects, work with faculty and students at Penn so that they can develop their creative output, and eventually they'll exhibit them locally in Philadelphia in a gallery that is closer to university. So I'm going to leave it very briefly here, and hopefully we'll answer, if you have any questions about our residency, you will stay until the Q&A session, and we will all together answer your questions over there. So now I'm going to pass it to our next speaker, Deidre, who is again the co-host of this event, and she will introduce us to the Perch and the research environment at Penn, where our residents can come and work. together, and then we will eventually hear from our three speakers who are going to tell you about their research. So Deirdre, I'm going to pass it to you.
Oh, thank you, Orkan, with sound. Hello, I'm Deirdre Krieger, lab coordinator for CodeLab, and I am going to share some of the perch space with you so you can see where the residency will take place and also some of our robots, and I will share a project that I've worked on. So let me share my screen. So this is the PERCH space, and PERCH stands for the Penn Engineering Research and Collaboration Hub. There are 3 robotics labs. This is not PERCH, that's Pennovation actually, but the video shows the Pennovation, and this was shot by Kumar Lab, which is one of the robotics labs that is at PERCH. So there's 3 labs that are housed inside PERCH, and there's Kumar Lab that focuses on autonomous ground and aerial robots, and it's headed by the School of Engineering Dean Vijay Kumar, and also is Mod Lab, which Orkan mentioned in his presentation, and is headed by GRASS Director Mark Yim, and they focus on modular robotics, micro and nano air vehicles, and personal robots. Code Lab is the 3rd lab that's in PERCH, and it's headed by Dan Kodacek, Alfred Fittler Moore Professor of Electrical and Systems Engineering, and it's where I've worked for the last 8 years. And it's a robotics legged robotics research lab, sorry. And in this video, you can see the interior space of PERCH and also some of the robots. So we just saw HQ Rex, and now we're looking at Rex, which is a 6-legged bio-inspired robot. And you'll also see Minotaur, which is a 4-legged, newer bio-inspired robot. And Fei Chan, who's now a professor at the University of Southern California and was formerly a postdoc with CodeLab, she worked with geomorphologists to develop sensors to research soil erodibility. So here we have a Rex robot, which is a 6-legged robot with a Minotaur leg mounted on it. And the Minotaur leg is being used as a sensor to sense the ground. And here's Minotaur bounding off into the desert. CodeLab PhD student Turner Topping focuses his research with Minotaur to develop new behaviors using the same simple controls and models in seemingly different situations. So the swinging leap crosses 2.5 body lengths using much of the same code as our door opening code. Integral to PERCH is the design and fabrication facility, also known as the machine shop, and it's on the 1st floor of the Pennovation Center. The facility is 1,450 square feet, and the artist in resident would have access to this facility in like the same way that our graduate student researchers have access to it. At the moment, the facility is only open to the staff, so just Jeremy Wang and Terry Kynes are allowed in there during the COVID times. I wanted to thank Dan Kodacek, who's the director of CodeLab that I just mentioned, and Sonia Roberts, a PhD student in CodeLab, and Turner Topping, because we had a lunch back in November 2019, and that was like a pivotal moment of, we were discussing how can we advance art and robotics at PERCH or GRASS, and we brainstormed different ways, and this came up as one of the things, and I was very inspired and approached Orkan, and that set things off into motion. So I'm very excited. about that. So in addition, I would like to also thank the SACS program for funding it and the co-sponsoring of GRASP and the Weitzman School of Design for helping it get off the ground. And also GRASP for being open to hosting artists in lab. It's amazing. I did want to share one of the projects that I had the opportunity to pursue while working with Code Lab. This is the pneumatic monument for women in robotics. It's a geodesic dome that's about 13 feet in diameter. And in my own art practice, I work with geodesic domes frequently. So it was a natural format to move forward with. And I worked in collaboration with Gabby Alfaro to brainstorm the project. And Gabby is part of the administrative support team for GRASP and also finishing her mechanical engineering degree at Temple and helped us set up the seminar. So thank you, Gabby. But we decided to created a STEAM project called the Pneumatic Monument for Women in Robotics. And we worked with Jeremy Wang from the machine shop again to develop. He created these 3D printed parts to help install the 2 different size triangles that are on the dome. And then when you enter the dome, there are 8 women pioneers in robotics that will greet you. And we worked with the GRASP faculty to figure out who should be featured in the dome. So it was a very collaborative effort. And here you can see Rujina Bautsky, who founded GRASP in 1979. And the portraits and quotes challenge stereotypes about who can be an engineer and allows young girls to start developing a sense of belonging in an informal STEM environment. I'll stop the sharing there. Thank you. I will hand off the presentation to Laya, and I'm excited to learn more about her work. Thank you.
Hello, everyone. I'm Laia Moga-Soldevilla. I'm an architect and new faculty at Penn at the Weizmann School of Design. I haven't had yet the chance to step into the lab, so I'm going to speak today about work at MIT and at Tufts University, bridging the gap between robots and material-driven design, and looking to digitally control biological materials and how that entails robots. So my work looks at how traditional fabrication, architectural fabrication materials like concrete, steel, glass, or ceramics have an impact in the way we in pollution and environmental ecosystems. And I'm looking at other materials and other possibilities to solve some of those ecological problems. So for instance, wood, skin, shell, or bone have incredible mechanical properties, perform much better than many man-made materials, and we yet have to integrate some of their properties into our systems. Let's say membranes that filter the environment, materials that change shape according to loads, or that have ability to propagate cracks and avoid breaking. So many of these properties are due to the way these materials assemble at the nanoscale and then grow into hierarchies. So I'm looking with material design and robotic fabrication at generating some of this so that we can get to these kind of arrangements inspired and effectively organized by understanding the nature of biological matter. In a way, to looking at how master builders like Le Corbusier with concrete, or Toni Gaudí with catenaric structures, or Alvar Aalto with wood, Preyoro with tensile structures, had this deep understanding of matter and fabrication, and then yet they could output proposals that were visionary and extremely interesting from the perspective of material and fabrication. So I'm going to share now a couple of projects. An old one at the MIT Media Lab, where we looked at water-based fabrication. And by that, we meant the way organisms and structures are assembled in water, in nature, and how that makes emerge complex structures. We looked in particular at shrimp shells, and this is a biopolymer that's super abundant on Earth and actually a byproduct of the fish industry, but it is mostly used in medical and pharmaceutical applications. So from a shrimp, let me check time, just to make sure I'm not over time. So from shrimp, you can deacetylize it through a process and get gels that can be cast into plastic films that now, instead of polluting our oceans, can dissolve in our sink with a bit of help. So that was super interesting to our research group. And we looked at scaling this up, going from what pharmaceutical and medical applications used, which were small tissue scaffolds or drug delivery devices, and go towards the robotic arm and larger systems of digital control for these materials. And what sparked this was the moment we saw one colleague at Harvard mold these materials into cups, into egg containers. We thought this was so interesting, and we wanted to take it to another scale. So our first approach was to engineer extruders so that we could extrude these gels on a digital and organized way, test our materials, see if they could mimic, materials that we normally use for extrusion. And we designed nozzles and different ways of working with this now water-based matter and all the constraints that this comes with. Soon we moved into more sophisticated systems, larger robotic arms and bigger footprints, and we designed multi-material extruders so that we could tune different properties of what we were making. And we made these giant leaves, from shrimp shell to a giant leaf that was supporting itself with structural inertia and was able to perform different functions, right? So wrap around wood, then open up like a leaf, then have this core of strength. So we were looking and investigating this way. How we did that was by digitally controlling the extrusion of these materials, by designing different thicknesses and hierarchies. I think the key here is hierarchy, looking at how a dragonfly wing is organized in nature and trying to understand those patterns and reproduce them with our robotic system. So, and I must say, only because we had that control and that type of robotic intelligence, we could make these structures emerge. So again, this is water-based. So in wet, it looks like that, but then when it's dry, it forms a very cohesive and strong material. And this is the small video showing the background of the project. So all of these crustaceans, they carry chitin in their shells, apart from other minerals and proteins, but chitin, this powder that you see, chitosan, can be combined with water and vinegar and make these gels that again are used in pharmaceutical and medical applications because they are biocompatible with our body. So our rationale was this is now compatible with the earth. It's a plastic that biodecomposes. So we were really interested in bringing this to larger scales and see how robust it could be. So again, we built this robot because it was the only way we could organize the material in a hierarchical way, like we saw in nature. So it was essential to this research was this idea of control through the digital system and the robotic arm. Of course, water-based systems need ventilation, need evaporation. So we built also a robotic ventilation system. We were looking at everything through a thermal camera to make sure that our materials were dry. And when we removed them from the substrates, we had this beautiful 3D shape now. From a 2D deposition, we were getting a 3D shape, again, because of this hierarchical control of material distribution and geometry. So now we have a 3-meter leaf made with one material and mediated by water. Water is mediating the material properties, the structural shape, and the natural degradation, because with some water, vinegar, or bacteria, anything that will attack the material, this decomposes and goes back to the earth. And some of the components of the system actually nourish the earth and can help plants grow. And again, once used, it can also be dissolved into a gel and now be used again in the platform. For architects, we were marveled by the idea that we had skin and structure in the same material system. So a bit of a metaphor for windows and beams, just by tuning the concentration of our polymer. And again, because we had the control of our digital platform and robotic system, we could now tune the material and look at different other printing strategies. Now, instead of having a robust beam, we could have a folding system into plastics and packaging and really beautiful folding systems. Intuitively, the next thing was, can we make the plastic bag that decomposes? Yes, we could, even if it took many more hours than you would like. This is a potential future where all of this could go into replacing, single-use plastic bags. Again, because we were controlling our platform, we could now not only print lines, but also print pockets of, instead of this, we could now print these little pockets and now have our materials drape and have this different weight. So we could look at fashion design, etc. And again, the qualities, the aesthetics of all of this emerged in an interplay of this material solidifying and our digital and geometric control by the fabrication platform. Again, because we were controlling our system, we could now think about composites and combine our matrix, our polymer matrix, with natural fillers and granules and fibers. In this case, this is cellulose pulp mixed. And now, instead of a stiff or a folding system, you have a very flexible, bendy, almost bending active system in your hands. All of this research and all the steps in between were exhibited at the MIT, but they are now at the Museum of Modern Art in the retrospective of our research PI, he was Mary Oxman, and they are now almost disappearing because this decay over time, and they are now very old. So another project I want to show you quickly is how I worked with other types of biological matter in the context of the Silk Lab at Tufts. They look at living materials for biomedical applications, and their matrix, I'd say, is silk, and they look at the two proteins that compose silk, fibroin and sarsen. Sarsen is going to be your glue, and fibroin is the protein that makes the fibers. So they look at the properties of silk, and they have a beautiful process of reverse engineering silk thread or silk cocoons into solution, into a watery gel-like solution, and then from there they fabricate tons of different instances, and all of this is silk. So they make screws that dissolve in your knee while they heal the bone cracks. They make hollow tubes that can replace veins, or microneedles for vaccines, electronics that you can eat, waveguides, microspheres, also plastic sheets relating to my previous work. So super interesting way of using silk as unexpectedly. So my work as a designer and an architect within the lab was to, again, scale this up, bring this material from an industry of medical and pharma to the industry of product and architecture parts, and by introducing, again, this transition towards the digital platform and the robot and the digital control. So in this case, instead of a very expensive robotic arm, what we were using was just hacking, let's say, a CNC carving system into an extrusion system that could just handle pressures and could extrude our pastes. These pastes were always based on silk, but silk is a fantastic protein that is able to encapsulate many things. In this case, just color, but it made these basketry systems that are perhaps half a meter wide, and they became my first project, and I really was impressed by the material and the control. So you could now imagine materials that have a base and then an added lattice, like you just saw, and you can make different patterns and flexibility. We can talk about this later, but from a very stiff system that was mostly piping and with chitin and chitosan to a very flexible now basket, almost basketry systems or fashion systems. This was very interesting to see how these materials were different. So by controlling again this platform, you could imagine anything, and differential geometries, transparencies, translucencies, control of feature size, of flexibility, of opacity. So really by incorporating this material intelligence into a robotic platform, we could expand into more futures. And again, the goal of all of this is to bring the properties that we see in biological matter by using biological matter and digital fabrication, so that we charge it with what we need, which is scale and robustness. And I am new, so if anybody wants to reach out and comment later after the webinar or in the future, I leave here my email, and I'll pass this on to our next speaker. Thank you very much.
Hello, everyone. It's good to see all of you here. I'm Cynthia Sung. I'm a member of the GRASP Lab, our General Robotics Automation, Sensing, and Perception Laboratory here at Penn. And I was just going to share some of the work that we do in computational design and origami robotics. So to start, we have a vision for the future, which is that in the future, any robot that you want to use in your own home or in your own lives, you will be able to make, whether or not you are an engineer. So here's an example. Let's say that you you have an idea for a bug-like robot that you want to crawl over some rocks. Well, using some algorithms and software systems, you would be able to input that information into some sort of computational design program, which would help you to figure out what are the engineering decisions that you need to make this robot a reality, so that you can very quickly bring this robot home and use it in the environment that you were thinking of. So the idea here is that robotics would not be just accessible to engineers and people who can design and create the robots and understand all the technology behind them, but really anybody who wants to make a custom robot can. Of course, this sort of system doesn't exist yet. And so what we're primarily interested in is what are the systems and algorithms and fabrication methods that we need to create in order to make this sort of system a reality. So I'm going to share some of the work that we've been doing along this goal, and more probably on the fabrication and origami side. But to give you a starting overview, this is the sort of idea that we're thinking of. This is a Build-A-Bot program that we're developing in the group. And it works sort of like a virtual Lego set. So you can click and drag parts into this 3D workspace and work on the 3D geometry of the robot. As you do this, the program keeps track of all of the kinematic and geometric constraints, and it'll make sure that what you are creating is valid. So once you've started to assemble this robot, then the system can suggest motions. It can simulate the robot for you. It can show you what the robot is going to do, so that you can then adjust the design according to your needs and make sure that the robot is going to function the way that you want. Now, once you're happy with this robot, then the system also incorporates any kinds of fabrication constraints, so that very quickly it can convert your virtual robot into a 3D design, including either 3D printable parts, fabrication instructions, electronic components, actuators, sensors, and control software, so that you can assemble the robot very quickly and have the thing that you had on your computer moving around on your desk. So this is our general pipeline that we're working on. And of course, in order to make this system work for a larger variety of applications and a larger variety of robots, there are a lot of questions that we have to answer in the group. So here are the technical challenge that my group is primarily interested in. I'm not going to go into all the technical details today. Instead, what I'm going to do is show you some of the results of the work. And if you're interested in some of the algorithms or engineering that is under the hood, then I'm happy to talk with you later as well. So you may have noticed that in the video I just showed, one of the primary assembly methods that we're interested in is folding. And so a lot of our work is motivated by origami and the potential of using origami as a fabrication method in engineering for fast and cheap and lightweight robots. You are probably familiar with some examples of origami in the world already. This is an example of a deployable lens that has been developed at Lawrence Livermore National Laboratory. This was a lens that they wanted to send up into space, but of course you don't want to send this huge thing up in a rocket, so you have to fold it down to a small size before you send it up. There are examples of using cardboard in order to make furniture, using folding in order to make window shades in different architectural examples, and even in medical applications using folding to get objects to go down in size so that you can get them into the body. As a roboticist, we're primarily interested in using folding as a way to make customizable robots easy to fabricate. And so here we want to take advantage of the fact that origami allows you to use a lot of planar fabrication processes and then fold a 2D shape into a 3D robot very quickly. So in that case, any kinematic structure that you want to create, we want to know whether or not you can create that using this very nice and accessible fabrication method. So in my group, we're primarily interested in exploring a lot of different folding designs to see what kinds of robots we can create. We have a database of different types of joints that you can fold. So here you see some examples of very simple joints that we've created that give you translational motion, that give you rotational motion. And we analyze both the motion and the mechanics of these structures. We've proven that if you can combine these joints together into robots of arbitrary structure. So what you're seeing on the right here is a robot that we lovingly call the penguin because it moves kind of like one. And it's assembled from basic origami parts that I showed you on the previous slide. The pattern right here is the pattern for the penguin on the right. And this entire robot was created from a single sheet of plastic. What's really nice about using origami as a fabrication process is that now we can also embed electronics directly onto the robot. So we can take advantage of the fact that the robot started as 2D to print circuitry right onto the center of the robot pattern. And when it's folded, that circuitry gets mapped onto the robot's 3D shape. So now we have motors and batteries and radio all embedded into the 3D geometry of the robot itself without a lot of assembly hassle. Of course, this robot took quite a bit of time to fold. I was already an experienced folder at that point, and it took me 6 hours to make this thing. So probably lots of people don't want to do that. And so in the lab, we're interested also in creating methods to get these robots to fold themselves. And so we work on a lot of self-assembly technologies. This is an example of a laminate-based fabrication technique that we use. When you expose the robot to heat, it'll self-fold in a matter of seconds. And then you can use the robot in its now 3D form in order to do a whole bunch of tasks. In this case, the robot is walking around on a flat ground. You can control it once it's folded. We got really excited about this fabrication method and we said, well, what else can we make out of it? And we were inspired by a lot of 3D printing technologies that use a layer-based fabrication approach. So using this exact same self-folding fabrication method, we created these structures that are basically layered and that fold into a solid 3D shape. In this case, you're seeing this sheet fold in boiling water into a fish-like shape that, again, you can control and have swim around inside of this tank. So these are different methods that we've been using to try to approach this question of, well, how do we make robots very quickly? How do we make customizable shapes very quickly? And how do we get robots delivered to an end user according to their specs, but not have to have them wait for a long amount of time for a manufacturing plant to create the robot for them. More recently, we've become very interested in the fact that these sorts of origami-inspired fabrication methods also allow you to make a lot of different compliant designs. So in this case, we have a whole bunch of layers that are stacked one on top of each other. And the fact that your pattern is folded gives you a lot of different degrees of freedom in the structure. So these patterns here are not self-folded, they were folded by hand, but they are the same sort of design where we have a whole bunch of layers stacked. And the folds allow you to squish the pattern. So now if you put tendons through it, you can get a lot of different types of very natural looking motions out of these shapes. And you can start to create interesting animatronic-like structures from a folded sheet. So we combined these two ideas and then we self-folded starfish, which you see here. This one is actuated by servo motors and tendons down the middle of each of the legs. And this starfish can achieve all sorts of different motions that we have models for, we have simulations for that we've created in the lab. And this Since then, we've also started to explore some different ways of getting or controlling the compliance in origami design. More recently, we've become interested in this bellows pattern, which you see in this picture right here. These sorts of structures give you controllable compliance. So you can make a robot that's either really stiff or really soft, and they allow you to store energy in the pattern itself. And what's really interesting, control the geometry of a robot in order to also control how it moves. So here, what you're seeing is this same pattern with a whole bunch of motors inside and electronics and a microcontroller on top. And when we compress the structure using the servo motors, then we store energy into the pattern, and that energy can be very quickly released to get this robot to jump and do some very dynamic motions. Now, if you change the geometry of the pattern, then you get different jump heights, or if you get the robot to be very soft, it might not jump at all. And so now you can control how the robot is going to move depending on how you design the robot insights and use them in order to design the patterns in the first place. So because of that, we have started an interesting new collaboration with members from COD Lab, who Deidre mentioned at the beginning, and they're very interested in legged locomotion. I'm not going to go too much into detail to this, except to give you a very quick teaser video, because Weishi is, I'll let Weishi give you all of the details.
Cindy, can you hear me? It's Deidre. Your screen is frozen, so I don't know if you can unshare and reshare.
I might have to leave and come back. So let me do that.
No problem.
I'm back. Can you hear me?
Yes.
All right, let me share screen again. Oh, it says host disabled screen sharing.
I made you a co-host, Cindy, so you should be able to share.
All right, well, let's see. I don't know when my slides paused, but I was on this slide. I was just saying that we are very excited that because we can tune the geometry of these origami patterns, now we can tune their motion and get them to do all sorts of really interesting behaviors that Weishi will tell you more about. So that was all I was going to say. A lot of this work is done by my lab members. Credit goes to them, as well as our wonderful collaborators. And if you have any questions about the things that we can do with origami engineering, or any of the underlying engineering techniques that we use, I'd be happy to talk with you after or answer any questions after the talks. Thank you.
Okay, hello everybody. My name is Weixi Chen. I'm a PhD student working with Daniel Kotychek in COD Lab under Grass Lab. And I'm going to continue Cynthia's talk on origami for robotics and talk a little bit about the projects we've been doing for the past couple of years. And here are all the collaborators that were on this project. It's a team effort. And so first of all, we're going to try to understand why, what's the compelling part of robots. So we want to build a dynamic robot that has high power and has high impact. So it can go anywhere, anytime with a programmable work inside of them. So we can also design the behavior. But the problem about this kind of robot is that most of the time, because of the high impact, it breaks down pretty easily. And that's why there's another part of robotics focusing on soft robots. So soft robots are robots that are pretty compliant. They're pretty resilient. They have a very robust structure. You can smash it, you can throw it, and it's not going to be broken that easy. However, most of the soft robots are, although you can tune the compliance, the stiffness, it's normally typically very slow. And so this is kind of like the two sides that we want to find an optimal solution to. So how can we make a robot that's both high power and high compliant? This is where we start to take a look at origami. Origami is a kind of metamaterial that has some sort of property that is not just the sheet itself. The geometrical structure will give it different kind of compliance, different resilient. And there's a lot of study on how to make origami and mathematical objects so you can design this with computational program. We're thinking, how can we use origami to help us build robots? This is the content that I'm going to talk a little bit about. So we're going to take a look at the origami module. There's two examples of how we're using this origami module for our robots, and then I'll draw the conclusion. So it all started when we decided that we're going to make a bobblehead kind of robot that is a camera stabilizer. So we use this kind of structure. We call it the Rebo. So we can use this structure and we can control it with tendons underneath it. But then we realized that the structure we fold is pretty stiff. So then we thought about, why don't we use this stiffness for something else? So we began to study this kind of structure. So this Rebo structure, it turns out that we can change some sort of parameters that we can define and get different kind of shape and different kind of stiffnesses. So we fold tons of different specimens according to this kind of pattern, origami pattern. And it turns out that by changing just one of their parameters, we can create a series of different paper spring. And these paper spring can exhibit some really good mechanical property that in the end, it's beginning to be very useful for us to build different kind of robots. So how reliable are these kind of specimens, these origami springs? It turns out that it's very repeatable. If you repeat it 1,000 times, it tends to go to it tends to go to a very stable linear part that it's repeatable. And we can also see that by changing the different parameters inside this origami spring, we can design different kind of stiffness, which is pretty important for a dynamical robot, because we want to show that different stiffness can achieve, and we can pick this different stiffness to do different kind of works. So here you can see that this is an example of, by tuning the different parameters, we show different stiffness that is achievable. After we realized that this origami spring is pretty good for generating stiffness, a spring-like motion, we made a Rebo juggler out of it. And by this we combined 3 different motors, and there's a tendon that goes all the way through the origami springs. We are able to juggle several different objects with this. So here we designed a very easy program that allow us to juggle a shot put that is 1 kilogram. And you see that this is a snapshot of our result. It can juggle this 1 kilogram shot put up to like 10 centimeters high, where the origami spring in all, the 3 origami spring takes only about 100 grams. So we did a lot of different experiments and show that we can juggle different kind of object. We can juggle a medicine ball, which is rubber ball that has sand in it. We can juggle a very heavy weight, that's shot put, that's 1.5 kilogram. We can juggle them to different height with a very, very low error. We also show that from different initial condition, dropping it at different height, we can control the same target to the same height that we expect it to be. Now, here's a video of what we have. So the fabrication, like Cynthia said, it's going to take a while. If you're pretty skilled, this whole origami spring takes less than an hour to fold. This is where dropping it at different height, it will achieve the same height. And this is where we can actually control once we have the jugular, we thought, why not turn it upside down? Once we turn it upside down, it became a leg. And this leg now face the problem of having having the need to lift its own weight up. So we did some re-engineering and then showed that this this robot is able to lift its own weight and jump high. We did some other testing and show that this robot is really capable of vertical jumping. And we also did some tests showing that by changing another kind of degree of freedom, we can control the robot to move forward. Here's another video showing the result. So we mount the robot on a boom that goes around, and we show that it is pretty capable of moving very fast. So I'm going to draw the conclusion. So in this project, we made this kind of origami spring, which we can design the compliance. It's easy to fold. It's very lightweight. It's very resilient. And it turns out that origami can make a very dynamical robot, contrary to most origami. Most people think about origami, they think about still object, they think about just like standing figures. But it turns out that origami is very useful for robotics. And we're still working on it. If you have any interest in it, you're welcome to contact me or ask any question in the Q&A. Thank you very much.
Thank you, Wei-Shi, for sharing your research. Now I would like to invite the panelists back, or everyone, so that we can quickly answer some of the questions that came through the chat. So we will take a few moments to, if you have any questions for our presenters tonight. And then obviously we are here for answering all the other questions about the residency. Hopefully the range of work today will give you a sense of how diverse the kind of applications and approaches to robotics can be, from the very technical side of things to more conceptual to more everyday applications of robotics. So please ask us questions, so that first of all, ask our speakers the kind of questions that you may have about their research, and then we will answer questions about the residency. I had two questions already on the Q&A. I think our panelists see the questions? I think one of them is for Laia. Maya, maybe you should answer the first question by reading the question first and then answering. Yeah.
Right. So the first question says, how long does it take to produce one of those large leaves? Well, so because this is a water-based material, it does take long. We want the biopolymer to align while it dries, and that needs to happen over time. So we tested many ways of accelerating that drying process, and it was affecting the mechanical properties of the system at the end. So we did use convection and room temperature, and that worked. But at the end, building one of those leaves, they have around, so they are 3 meters long, 1 meter wide, and they have around 5-6 layers. That means that it can take 5 to 6 days. Right, because we want each layer to be fully dry before we apply the next. So that's ideally in an industrial production system, this could be for sure, I think, accelerated. We were conservative, we were very, let's say, careful with our system, and it did take long. I think I see another question about the material. Can you comment on the drying kinetics of the chitin gel and need for thermal uniformity to retain form and structural integrity? Similar question. So the chitin chitosan gels, they when we were looking at the thermal camera, we just were looking for evaporation. We were looking for it to be cold. So we knew it was evaporating as water still. We still wanted the material to be a little bit wet when we popped it up from the substrate so that it would take final shape. So the interstitial water within the molecules would still be there so that it would fold and find this 3D shape. And the key here, the key of this kinetics was the substrate. So we tested wood, we tested polymers, we tested silicones, but by using anodized aluminum as a base, we ensured that the material gripped, and this is because of charge and water tension at the interface. Anyway, we made sure that it gripped during drying, and then that it popped still a little bit wet. So no heat, just convection to make it work. I think I see a question for Wei Shi.
Okay, so here's a question from James. What software do you use for creating parametric design models? So for the origami pattern, we use MATLAB to create it. We wrote a program that's very simple. You can enter the parameters you want, and it will generate a folding pattern. And then we took it to a laser cutter. So we cut out the outline, and we perforated the folding lines, and then we fold it by hand.
I think I see another question about the chitosan-based bags. So as I said, it is in the right conditions, we can dissolve these materials. So for instance, the plastic bag, you would put it in your sink, add vinegar, like acetic acid 4%, and it would turn into a gel. So by humidity, by condensation in a water bottle, it would not dissolve, it would swell. Same with rain, it would swell. So what we did to overcome some of these was beeswax on top of all of these systems and prints, so that now they would still decompose with bacteria and acetic acid, but they would withstand sweat and rain and small amounts of water. Of course, submerged in the ocean, they would eventually disappear.
We have a question for Cynthia.
There's a question from James. What actuation were you using to move your folded bots? So we used a variety of actuation methods. It depends on what it is, what scale the robot is at, and what we're trying to do with it. Some of the examples that I showed, we used servo motors. The smallest self-folding robots, we use magnetic fields. So we put magnet or magnetic particles into the fold pattern itself, and then we use external magnetic coils to move the robot around. And then some of the larger ones, like the one that Wei Shi was showing, we use DC motors brushless or brushed. And then there's one more question. What other barriers do you anticipate coming across as you work to make robotics construction more accessible? So I think there are a lot of interesting questions and a lot of interesting challenges in making robots easier to manufacture. The main one is, how do you put your actuators and sensors and electronics in the mechanical structure of the robot, right? So normally when you think about building a robot, you have the structure, right? You have either the origami pattern for us, or maybe the metal components that make up your arm, or like wheels if you're making a wheeled robot, and those are all mechanical parts. And then you have your motors, you have your sensors, and you have your electronics. And so those all need to be assembled together. And figuring out how to place everything properly would be a challenge for automated assembly. Right now, it's we do a lot of that by hand. And so a person can go in and visually inspect the robot and make sure that everything was assembled properly, but getting everything to align is still a challenge. Weishi, I don't know if you have additional comments.
I think that that says it very well. I would like to add that actuation is a very huge part of the robots. So now we're using DC motor for my dynamical robots. But in the end, we would like to have some active material to replace the DC motor, which is very heavy. And hopefully we can make a lighter weight robot.
Yeah, there's a couple of other questions coming to the list, but while you're looking at them, I also want to interpret Aaron's question in a different way, because you both mentioned that you're really motivated to make robotics accessible to other people. So what other, beyond the technological limitations, what other things do you think are making it not so accessible today? Other kinds of constraints that you're navigating as researchers, social constraints, cultural constraints shaping your work? Cynthia, any comments?
Sure. So I think there are a lot of different factors that go into making robots more accessible. So we're primarily interested in the engineering side. How do you make the design process more accessible? Mm-hmm. Even within that question, making it so that a person who is not familiar with the engineering design process, so that they can actually specify a design, that's a huge challenge. Mm-hmm. So if I'm an engineer and I'm talking to another engineer, I know I can say I need a robot that fits within a certain volume, it has certain load-bearing constraints, it follows certain trajectories, all of that stuff. And I have a sense of what kinds of constraints I need to specify in order to make a robot design functional. Making that sort of specification accessible to a non-engineer would be huge. From the zooming out from the design focus standpoint, there are also questions, as you said, about cultural viewpoints of this process. So not everybody wants robots to be readily accessible and easy to make for in everyday life. And so trying to figure out how we can address concerns about safety or security and all of that is a big question that my group does not really deal with, but I think it's a very important question that we would need to think about as we start to try to make these technologies more accessible to the general public.
We have one question that might be actually a follow-up coming from the audience. I'm reading, everyone on the panel produces interdisciplinary work combining technology and science with art and design. What is everyone's advice for someone who might only specialize in design but wants to get into more interdisciplinary work, even if they have no experience in robotics, biology, and so on? I think this question is important because we may have artists, designers applying to the residency with not having enough technical background. They may feel like they don't have enough technical background. What would be your advice for them to work in an interdisciplinary environment or working with engineers and scientists like you who are very advanced in the subject matter with lots of years of background?
You should apply for the artist residency program. I don't, you two, the other two may have some more comments on this, but I think the best way is just to reach out and to see and to get your hands wet, right? To try a project. A lot of the reason why I'm interested in doing this presentation, and probably the other panelists are also interested in doing this presentation, is to interact with all of you. So if you have an interest in learning more about the technology, learning more about engineering and design, then we would be happy to talk and see where would be a good starting point to get the projects that you're interested in doing going.
I must say, in my experience as an architect, I came to, a living materials laboratory or the MIT Media Lab with more like the question, with a design background, and we always joke with my partner, this is layer by layer that you get, that you get to incorporate different disciplines by going to courses, but as Cynthia said, collaborating. And by collaborating, you realize which is the amount of knowledge you need to carry this on. And sometimes is for a designer at least, is the good enough knowledge to communicate with the engineer, to communicate with the scientist, so that we speak the same language. And that's crucial. And I think I would have loved to do another degree in bio, another degree in computer science, but by surrounding myself with teams, we could make all of these projects happen without all of us being a specialist in everything.
Yes, I would like to add on that engineering is not a very like high bar kind of thing. The main goal of engineering is to try to problem solve. And so you have a problem, you take the problem here and we try to solve the problem by all means. And I would say don't worry about the background. People will like to work with you for your background, and with the help of everyone being able to know everything from every different disciplinary, you can generate something that's very very interesting.
I think William is asking something similar. I think with regards to the residency, right? He says, with the residency, will I be able to collaborate with people and apply knowledge into my proposal? I don't have a degree in science, but a strong interest in working with researchers. That's part of the program, correct?
Yeah, so what we don't expect, obviously, people coming with a very technical background. We expect researchers, we expect an open-mindedness towards what research is and an investment in some of the technical questions that are coming with robotics. But obviously, it's a merger of art and robotics. So we at Penn will hope that we will create an environment as advisors, as faculty, as students who can get involved with other these researchers' work, so that the work can be co-developed in collaboration with the applicants. So I think we outlined a couple of entry points in terms of conceptual starting points as the themes of the residency, but ultimately the proposals are going to come from the residents, and we'll try to match who would be the best support group for that proposal to be realized. It's not a very long time to develop year-long research initiatives, but it's very important to match the right skills so that it will become a very productive collaborative process with an exciting outcome. We cannot solve all the problems in a residency, but really use robotics to ask really interesting questions about lots of issues, from the environment to the social issues.
There's actually someone asking about capitalist structures. He says, how do you think biomaterial construction benefits current capitalist structures? How do you think biomaterials can help these structures break down? Yes, We were commenting the other day in one of my classes about biological materials and architecture. We were commenting on concrete and how concrete is a huge problem because of its ecological footprint, but it's not because the material is a disaster. It's because it's used so much and so intensely in architecture. So just by introducing hemp fibers, fillers within concrete that provide it with other properties or that help its structure, we subtract some of the concrete and we add some biological material that decomposes over time with no issues. And that's it can have a huge impact because of how much concrete we use. So yes, I think biomaterials and biological matter, mushroom bricks or bacterial leather will not make housing, but it will be introduced into the materials that we know and love and change the way they decompose and they are used. For instance, there's a DARPA call to architects for the first time. This agency is calling architects and telling them, how is the living house of the future? How do we make houses that self-heal, that produce energy, but really looking at nature and how nature does it, and how do we apply this to construction? So yes, I think they will have an impact in capitalist structures, as you call it. I think that was the last one.
Yeah, we went through all the questions. We can wrap up or give one more minute for last minute breaking questions to the panel, or the panelists may comment on each other if you have. It was really great to first of all learn everyone's research more in detail. I'm very impressed by the range of depth that was covered in the presentations, because we have sometimes high level, sometimes very low level, down to the equation side of things. But that's the nature of working with a technological subject matter. It's important to respect the difficulties and the advanced knowledge that's required to understand things, but also through collaborations, it's possible to access this knowledge, to access this information by working together on complex subjects. So hopefully people who would apply to our residency will get a sense of both the difficulties and also the exciting parts of robotics, and develop a critical eye for it. So I think we will probably wrap up here. Is there anything else that our panelists want to add? Deirdre, would you like to add anything about the residency?
I would say to artists or creatives or whoever's interested in applying, that really look at more in depth the projects that are happening on GRASP. The website is very detailed and it's new and it's interdynamic. So I would strongly urge you to look at what is happening, how are we working with geomorphologists or other people. And I mean, robotics is very collaborative and interdisciplinary, and there's lots of ways you might see yourself fitting in. And I think the question for the residency, think about how you can use the robotics projects to address the themes that we were talking about that are social, cultural, educational, environmental challenges. So that would be my advice. And if anybody has more questions, please go to our website and hit us up. It's at residency.cs.upenn.edu. I also am very grateful to all our speakers tonight. Thank you so much. I love hearing about your work, and it's always exciting to me, and that's why I'm so excited that we're going to get artists in Perch, and that's it. Thank you, Orkan.
Yeah, thanks everyone. Again, thank you for joining us, and we'll organize probably one more webinar in a couple of months. We pushed the deadline of our applications. It was February 15, but we pushed for 3 months because we want this to be a on-site residency, so that we, instead of starting in the fall, we'll push it a little bit further down the road. So current students who are graduating may become eligible for application. Right now, the residency is not open for current students. So this comes as a question all the time. We receive lots of emails about this. students can definitely get involved with working with applicants who are not residents. You can support their work, you can do collaborative research, but we really are looking for practitioners who are outside the school for a couple of years so that they have a body of work to apply with. Again, come check our website. We'll keep things posted. We'll have a mailing list so that you can subscribe. But when the pandemic allows us to come back to the studios to perch, we will kick off the residencies and do amazing work. Thanks again for joining us today, and hope to see you in our other sessions. Please ask us questions over email through our website. Thank you.
Thank you.
Thank you.
Yeah.